Well, thank you very much for organising this meeting. This is going to be a talk on the muon-fluorine interaction, a model for exploring decoherence. And I particularly want to thank John Wilkinson, my PhD student here in Oxford, who made a crucial contribution to this work. But also some of the experimental data was taken with the assistance of Franz Lang, Tom Lancaster in Durham, Francis Pratt at the Rutherford Lab, and a number of others. So what I'm going to be talking about today is the way in which a system and its environment interact. So very often in thermodynamics, we are considering a system and an environment. The system is well defined and understood, the environment less so. So typically the way this works is that the system and environment joint system will evolve together, but the von Neumann entropy of the joint system and environment stays constant. You can work this out simply using the density matrix of this joint system. Okay, but the system will decohere because of interactions with the environment. So you can follow this by working out the density matrix of the system by just tracing out the environmental degrees of freedom. And that means that the entropy of the system increases with time. The problem that we often have is that the environment is large and not so well defined. So one example that I'm going to present is something known as the F-mu-F state. If you implant a muon inside a fluoride, very often what will happen is that the muon will get very close to some fluoride ions. These are highly electronegative, they attract the positive muon. And then what happens is you have a coherent oscillation that you can observe if you just look at the time dependence of the muon spin, which arises from the magnetic dipolar interaction. This was discovered nearly 35 years ago. It gives rise to this well-defined signal that you can see here. It occurs in lots of different materials, so you can take various non-magnetic iron fluorides like the ones on the right, or also Teflon, PTFE, shown in the curve on the left. No magnetic field is applied here, there's no magnetic order, it's just simply the muon exchanging polarization with the fluoride nuclear spins. You also see it in a whole range of molecular systems, so these are various molecular magnets, and in all of these three cases you see these characteristic oscillations, which gives you a lot of information about the implanted muon state, its distance from nearby fluorines, whether it's 1 or 2 or fluorine and a proton, and it gives you a great deal of information. Now, there is a problem with this whole approach. Even though fluorides have been studied with muons for a long time, you have this coherent function which looks very beautiful, but right from the beginning, from the 1980s, it was noticed that you had to multiply this function by an empirical function, some kind of stretched exponential. And whenever you see a stretched exponential, you know that something is missing. You've missed some description of the physics. And so in this talk, I'm going to really tell you how you can understand this in much more detail. So let's just start with something like the F-mu state. If you have a fluorine and one muon, those two spins give you essentially 4 energy levels, the transitions between which give you these kind of oscillations. And this shows you a theoretical calculation of this effect. If you put another fluorine in, you now have a Hilbert space of dimension 8. You actually have 4 doublets. The transitions between those give you these characteristic oscillations. Now, if you take something like calcium fluoride, of course, what basically happens is when you put a muon in, the muon sits between 2 fluorine ions. But of course, there are a lot of other fluorine ions in the crystal. And what I'm showing here in colouring in the various shades of blue, not only the nearest neighbour fluorines, but the next nearest neighbour fluorines as well. And I want to consider those. So to evaluate this, you have to look at the muon interaction with its nearby neighbours. This is a dipolar Hamiltonian. You can work out the polarization just by working out the density matrices, but the problem that you have is that the Hilbert space is big. So for example, for m spins, it takes this form, and this grows exponentially with the number of spins. So if you take the F-mu-F state, you only have these transitions that I mentioned. You can plot them in this little diagram that I've got on the right. The size of the blob tells you the strength of the transitions. Now, if you add the next nearest neighbour fluorines as well, those 4 energy levels on the left turn into 4 broadened energy levels. And then similarly, the the structure of those transitions all blurs out as well. So those transitions move to these transitions. And of course, the effect of this is to cause the oscillations to decay. So if you just concentrate on the red curve is just looking at the nearest neighbor fluorine interactions. If you now add the next nearest neighbors in as well, you see that the oscillations start to decrease. And you can see this in the thermodynamics as well. If you work out the muon entropy, and indeed the fluorine entropy, maybe just concentrate on the red curves in the middle. For the case of F mu and F mu F, so this is just nearest neighbor interactions, the entropy of the muon oscillates, but adding together the next nearest neighbor muons, you can see that the entropy of the muon is now rising to a maximum, and it never recovers down to its zero value that it had when it was in a pure state. So you can use these insights to try and think about these decoherence relationships. One of the ways we have been thinking about this is if you look at the second moment of the field distribution, this is just the Van Vleck formula, each nucleus contributes to that second moment at a rate given by 1 over r to the 6, so it decreases very quickly. The problem is we want to sum over all the nuclei in the crystal, which means that sum has to go out to infinity. And the way we found of sorting this out, even though we can do that sum to infinity, we can use a parameter lambda to scale up the next nearest neighbor interactions in order to mimic the effect of all of the nuclei in the crystal. And it turns out this scaling up doesn't have to be done very much because of this 1 over r to the 6 interaction. So in fact, it's only a change of about 6 or 7%. But this small 6 or 7% change in that contribution allows you to estimate everything else. So let's go back to calcium fluoride. We choose calcium fluoride because the calciums have no nuclear moment, essentially. So you add the muon. The muon will actually cause a distortion, which we can calculate through DFT. So what happens is it brings those nearest neighbor fluorines in. And now what we're going to do is look at the connection with those next nearest neighbor fluorines. We can now do a fit based on just the effect of next nearest neighbor and nearest neighbor, and it works perfectly with the data. This essentially has only two fitting parameters. One is the amount which those two nearest neighbor fluorines, the dark blue spheres, move in, and the other is this parameter lambda. And it turns out that both agree with our theoretical predictions on the basis of DFT and on the basis of doing the Van Vleck sum. To show that this effect works, in another context, we've tried sodium fluoride. In sodium fluoride, there is a nuclear moment on the sodium. And so this, and also the sodium, has a 3/2 spin. In sodium fluoride, you put the muon in, it has a site here, and what it will do is it will pull in the two nearest neighbor fluorines and actually push out the next nearest neighbor sodiums. But we can do the same calculation again. We actually fitted the data from the 1986 paper, and you can see again, without the correction due to decoherence, you get the red dashed line. With the correction for decoherence, you get the blue line. Again, only two parameters in that fit. One is the amount to which the blue spheres move in. This is calculated through DFT and agrees perfectly with those calculations. So that isn't really a fitted parameter. The other one is this scaling up lambda effect, which we can also work out from the Van Vleck sum. And you can see that it works perfectly. So in conclusion, we've got an approach to understand the decoherence from all the fluorines and all the other nuclei in an infinite crystal, and to solve this problem that's really quite hard. As Jürgen reminded us right at the beginning, these problems with systems where you have enormous Hilbert spaces are very tricky to calculate. Here is an approach where you can really see what's going on through the experiment, and you can get very good agreement with data, even though you're using a restricted set of nearest neighbor fluorine ions. So I'll finish there. Thank you.
Thanks, Steve. Do we have any questions? Okay, so I'm wondering, does this approach work? Does it fit the data better than adding a stretched exponential empirically, or do they more or less?
It actually does. So in fact, if you go back to the calcium fluoride data, where we've got data which goes out to very long times, it does a much better job than a stretched exponential. And of course, the problem with a stretched exponential, or even if you use a Lindblad formalism to mimic further interactions, you've got parameters and where you have no idea where they come from. They've got no physical origin. Whereas the great thing about this approach is this additional relaxation is coming from incredibly well-defined physical interactions that you can compare with theory. So it's you know, the model is sound, whereas with a stretched exponential, you are waving your hands in the air.
Mm-hmm. There's a question here from Jürgen Schnack. Could you use Ewald sums for the infinite sums?
Yes, you can do that. You can use Ewald sums for the infinite sums, and we do this with dipolar interactions. The great thing with these 1/r⁶ sums, though, is that they converge so quickly that you don't really need to bother. You can do it straightforwardly without having to use Ewald sums.